Welcome to all of you in Quantum Mechanics lecture series. Myself, Professor Dr. Arvind Sharma, HOD Physics, Government Lohia College, Churu, Rajasthan. Today's topic of lecture is WKB method. WKB method is known as, according to their innovative scientists, Wenzel Kramer's brilliant approximation. And in short, it is called WKB approximation. It is a time-independent approximation method. It is a time-independent approximation method. Now, in which kind of situations it is applied? The situations where potential energy is slowly varying function of position. WKB method is applied to the problems where potential energy is slowly varying function of position. That means potential energy varies slowly with respect to position. In such kind of problems, this method is applicable. Okay? By using WKB method, we can solve one-dimensional problems and also three-dimensional problems which are reducible in one dimension, that is radial part. It can also applicable to three-dimensional problems which can be reducible in the one-dimensional radial part. Okay. Now, what is the meaning of slowly changing potential? A slowly changing potential means there is variation in the potential energy with respect to R, slightly over several wavelengths. And which kind of wavelengths? De Broglie wavelengths of the particle. Okay, and I am again repeating it. What is the meaning of slowly changing potential? The meaning of slowly changing potential you can understand from here. Variation in potential energy VR slightly over wavelengths of the particles or de Broglie waves. Okay, so this point is very important for this approximation. Okay, and it is also shown in figure here. Here we see that slowly changing one-dimensional potential. In this figure, it is shown. We can easily observe x-axis is x, y-axis is v. Okay, v versus x plot, and if the value of E is here and potential is slowly varying here, and this difference is E minus V. So these show the slowly changing one-dimensional potential. And upper curve, that is for associated wave function. Okay. Now, because approximation needs to explain the de Broglie wavelength, so first of all, what is the de Broglie wavelength associated with a particle moving with energy E? A particle moving with energy E, then what is the expression for de Broglie wavelength? In a region where potential is V, energy is E and potential is V, de Broglie wavelength of such kind of particle is given by the expression lambda equal to h upon p. Simple, but p is given by under root 2m e minus v, because we know that half mv square equal to e minus v. From here we can easily calculate p equal to under root 2m e minus v. Okay. Now the propagation constant. You are all familiar with propagation constant k. K is 2 pi upon lambda, and if we replace the value of lambda, so this expression comes k equal to under root twice m e minus v upon h cross or h cut. Okay. Now the main condition that is imposed for the WKB method, mathematically slowly varying potential, can be expressed by the condition, because this is the main condition for potential. Slowly varying potential, and it can be mathematically given by the magnitude of 1 upon k square dk upon dx less than 1. This is the main condition for WKB method, because it can be applied only for slowly varying potentials, and mathematically it is given by 1 upon k square dk upon dx magnitude less than 1. And if we replace the value of k from here, then this condition becomes here in terms of h cross m del v upon del x magnitude upon 2m e minus v raised to 3 by 2 less than 1. And in terms of lambda, it is given by this expression lambda delta v upon dx upon 4 pi e minus v less than 1. Okay. So this equation gives the validity of WKB approximation. These conditions, this condition should be necessary for the validity of WKB approximation. Okay. Now, principle of the method. Principle of the method. WKB method consists. What it consists? We need to introduce an expansion in the powers of h. We need to expansion of the wave function in the powers of h cut or h cross, and neglecting the higher order of h cut. Okay, this method needs expansion of wave function in terms of powers of h cut and neglecting the higher powers of h cut. Neglecting the higher powers. Now, Schrodinger equation, at least in some regions of space, is reduced to classical limit. We know that Schrodinger equations in some regions of space is reduced in its classical limit. However, method has a wider range of applicability than the classical approximation, because we know that the procedure can be carried out even in regions of space where classical interpretation is meaningless. Schrodinger equation can be applicable to such kind of regions also where classical interpretation is not possible. That means it is meaningless. And such kind of problems you already done in UZ classes. The region E less than V in inaccessible to classical particle. Okay, if incoming particle energy is less than the potential, then according to classical mechanics or classical interpretation, it is meaningless or inaccessible. But according to according to Schrodinger equation. According to Schrodinger equation or quantum mechanical, it is possible to explain such kind of problems, and you already see such kind of problems in your UG classes or in your first semester. Now let us psi x be the wave function which satisfies the Schrodinger equation. And the Schrodinger equation here given by this equation, one-dimensional Schrodinger equation, del 2 psi upon del x2 plus twice m upon h cut square e minus vx psi equal to 0. The well-known solution of such kind of problems here, psi equal to c e raised to iota phi x upon h. Psi equal to c e raised to iota phi x upon h cut. Here c is constant, here c is constant, and phi x is yet undetermined function. Here, if we want to solve such kind of problems, we should determine or we should have some function about phi x to solve such kind of problems. Okay. Now, if this is a solution of this equation, this is a solution of this equation, then we need del 2 psi upon del x2, that means psi double dash, and it can be determined from here easily. Okay, by double differentiation. First differentiation psi dash, second differentiation psi double dash. Okay, and the terms coming in the expression phi dash and phi double dash are well known notations. Okay, so from here we get the result of psi double dash equal to this. You just replace psi and psi double dash from 5 and 7 into equation 4 and rearrange the equation by taking this constant outside, by taking this part outside, and remaining part is this. As we know, because psi is given by this, we are taking the solution of psi equal to c raised to iota phi x upon h cut. It should not be equal to 0. Hence the remaining part of this equation, because product of two parts is equal to 0, one part is not equal to 0, then other part should be equal to 0. So this part is equal to 0 and equation is here. Iota h cut phi double dash minus phi dash square plus twice m e minus vx is equal to 0. And now the method is applied now here. The WKB method coming into the role. Approximate solution. Now we need to solve it for approximate solution, and here we apply the WKB method. For this, expand phi x in terms of powers of h cut. Okay, and this expansion is given by phi x equal to phi 0x plus h cut phi 1x plus h cut square upon factorial 2 phi 2x plus so on. Again, I am repeating because this is the most important part or most important turning point of this article, most important key point to be noted. Phi x equal to phi 0x plus h cut phi 1x plus h cut square upon factorial 2 phi 2x plus h cut cube upon factorial cube phi 3x, so on. Okay, so you remember this expression, it is necessary, where the subscripts phi's are independent of h cut. Subscripts phi's are independent of h cut. It is very important condition, should be remembered. Now suppose we assume smallness of h cut. We assume smallness of h cut, then first two terms are sufficiently sufficient to give the sufficiently good or better results for approximation of 5x because of smallness or low value of h. Okay. Now we here see that if we want to solve this equation, we need the expression for phi double dash x and phi dash, and it can be deduced or it can be calculated from here easily. So in next term we calculate phi dash x and phi double dash x, and we just see there is nothing, only dashes are here, and in the next equation double dashes are. All equations are same. All equations are same. All three equations are same, only changes are single dash and double dash or without dash. All three equations are similar. You just put these equations. So we here, after replacing the three equations, this is the main equation, from where if we rearranging the equation in the part of coefficients of powers of h. You just rearrange this equation in the powers of h cut and their coefficients. Okay, so this equation becomes like that up to second order h cut. We are only considering up to second order h cut, that means h cut is square. So first term is without h cut, second term is h cut, third term is h cut square. So this is the equation. Okay, in order that equation 11 may hold identically in h cut. This is the equation 11, and if it is hold identically in h cut, the coefficient of each power of h cut should be or must vanish separately. If this equation hold identically in h cut, then each power of h cut, that means h cut 0 power, h cut 1 power, h cut 2 power, there are three terms, and their three coefficients independently or individually equal to 0. So this requirement gives series of equations, and here we are only taking three coefficients. So we have three equations from this condition. Equation A from h cut 0 coefficient, equation B from h cut coefficient, equation C from h cut square coefficient. Okay, and so on. We can easily obtain the h cut cube, h cut 4 coefficients also, if we considering the higher order terms. Okay, now these equations may be solved successfully. Okay, so first equation defines phi 0. We easily see that from here phi 0 can be easily calculated. Okay, in terms of e minus 1. The second term gives phi 1 in terms of phi 0, and third term gives phi 2 in terms of phi 0. Okay, so from equation 1, phi 0 dash equal to plus minus under root twice m under root e minus 1. Phi 0 dash equal to plus minus under root twice m e minus v. Now integrate both sides. Integration of above equation from both sides gives this equation, and integration limits are x0 to x, from x0 to x plus minus. Okay. Here x0 is arbitrary fixed value of x. X0 is arbitrary value of x, which is fixed value. Similarly, from b equation, phi 1 dash equal to this, and this equation yields, if we integrate it, phi 1 equal to iota upon 2 log phi 0 dash plus c1. Okay, c1 is the integration constant. The result is inconvenient if phi 0 is negative. If suppose phi 0 dash is negative, then we know that logarithm of negative function differs only by an imaginary constant. If a logarithm of a negative function and it differs by an imaginary constant from the logarithm, so we replace the equation by phi 1 equal to iota upon 2 log phi 0 dash magnitude plus c. We convert this part to the magnitude of phi 0 dash. Okay, due to the concept that logarithm of a negative function differs only by an imaginary constant from the logarithm of the absolute value of the function. Okay. Here C2 is arbitrary constant. Similarly, phi 2 is given by this equation. Phi 2 is given by this equation. It can be easily calculated from the equation C above. Okay. Now from equation 16, we see that phi 1 is represented in terms of logarithm of phi 0 dash. Okay. Phi 1 is represented in terms of logarithm of phi 0 dash. Therefore, it not in general small compared to phi 0. It is not small. This part is not small. Hence, we must retain the phi 0 and phi 1 terms to solve this equation. We cannot neglect the term phi 1. It must be considered here. Okay, so we retain the terms phi 0 and phi 1. Okay, on the other hand, from equation 17, we see that phi 2 will be smaller, where whenever delta v upon delta x is small and e minus v is not too low, close to 0. If we see this equation, here we see delta v upon delta x is, if it is small and e minus v is not close to 0 in both cases, the term is can be negative, because delta v upon delta x is small, this is small, and this is not close to 0. So this term can be further. It can be easily that smallness of higher approximations. Smallness of the higher approximations. Phi 3, phi 4, and it requires the smallness of all derivatives of v, because these functions contains the derivatives of v, delta v upon delta x, or such kind of derivatives. Okay, thus WKB approximation. Hence, WKB approximation will be suitable in cases where V is sufficiently smooth and slowly varying function of position. What is the condition? For WKB approximation, where it is suitable, where V, potential energy function, V is sufficiently smooth. Number one is smooth, second slowly varying function of position. There are two conditions. First, it should be smooth, and second, slowly varying function of position. Okay. Now, the approximation method WKB solution. Now, the approximation WKB solution of equation 8 may be expressed by taking both terms. First term is phi 0, second term is phi 1. It is given by 1 upon 2 iota h cut log magnitude of phi 0 dash. Okay. Here, the constant C2 is absorbed by phi 0. That means we included or incorporated the constant C2 in phi 0. Okay, so it is absorbed by the C2 constant is absorbed by the phi 0. Now just substitute the function phi x from equation 18 in equation 5, where psi equal to c e raised to iota phi x upon h. Okay, so approximate solution our approximate solution becomes like this equation: psi approximation equal to c twice m e raised to minus vx raised to minus 1 upon 4 exponential plus minus iota upon h cut integral x 0 to x under root twice m e raised to minus vx dx. This is the expression for approximate solution, okay, where C remains arbitrary. Here C remains arbitrary. Now, two solution contents in 90. In this equation, two solutions are contained because there are plus minus sign here. Okay. So, normally, like as in superpositions, suppose first term we are taking plus multiplied by constant a and second term minus multiplied by constant b, and we just had the both solutions. So these differing signs in the exponent are linearly independent. These are linearly independent. So the approximate general solution. So the approximate general solution for WKB approximation is given by psi approximation. First term is A and solution is here plus, and second term multiplied by B for the negative sign. A and B are arbitrary constants. Here A and B are constants, arbitrary constants. Positive exponential corresponds to wave moving in the positive direction. Positive exponential, this is positive exponential moving towards positive direction. This is negative exponential wave moving in the negative direction. For the special case, suppose we are taking Vx is constant. So these approximate solutions reduces to the plane waves. These are like e raised to iota px upon h cut from here, and exponential minus iota px upon h cut from here. Okay. alternate form of equation 20. What is the alternate form of this equation? Alternate form of this equation, expression given by psi approximate solution equal to C twice m e minus v raised to minus 1 by 4 cos iota upon h cut integral x0 from x0 to x under root twice m e minus v x dx plus theta. This is the alternative solution. This is the alternative solution where c and theta are arbitrary constants. Okay. So these approximate solutions. So these approximate solutions 20 and 21 of the Schrodinger equations are called WKB psi functions. These are known as WKB psi functions. Equation 20 and 21. These functions known as WKB functions. Okay. These are the solutions of Schrodinger equation and known as WKB solutions. And next lectures we are going to connect formulas for penetration of a barrier and barrier problem and alpha decay problem. Okay, so in next lectures we are going to learn about the applications of this method. Okay, thanks to all of you.